Uh, Broadly speaking, we now discuss the directional derivative. So this is a generalization in a sense of the partial derivative with respect to some variable. Okay, when we get there, you'll realize what the directional derivative is all about. In what sense is it the generalization of the partial derivative? Okay, first of all, let's suppose that we have a function phi, which is a function of several variables, maybe just xy or xyz, etc. So for now, let's suppose it is a function of three variables, x, y, and z. We know that the grad operator is defined as, so in this case your grad of phi is defined as the vector containing the derivatives of phi with respect to the variables x, y, and z respectively. So this would be the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, the partial derivative of phi with respect to z. And of course this operator grad can be generalized to 2 variables, to 4 variables, etc., etc. Sometimes this is written as a dot product of two things. Well, let's for now leave it as it is, because in the next section we will discuss a number of operators dealing with these derivatives. Okay, so now suppose that we have that the function phi is a function of 3 variables x, y, and z, and previously we discussed the fact that we could take the variables x, y, and z as being functions of t, or separately as functions of the arc length variable. In that case, if we were to do the derivative of phi with respect to the arc length, then by the chain rule for multivariables, we have that d phi ds is going through the various arms of the function phi is the derivative of phi with respect to x times the derivative of x with respect to s plus the derivative of phi partial with respect to y, the derivative of y with respect to s plus the derivative of phi with respect to z partially, and the derivative of z with respect to s. Well, as a result of that, we notice that we could write this as a dot product of two things. If you look closely, this is then, as the first vector, we could have the derivative of phi with respect to x, comma, the derivative of phi with respect to y, the derivative of phi with respect to s, dotted with the vector dx ds, dy ds, dz ds. So if you just take the two dot products, you know what that is about. You multiply the various coordinates and add those various things up. Now once we write it in this manner, it's clear that this is now, or can be written as the grad of phi, because this first vector really essentially is the grad of phi dotted with the vector dx, ds, etc. So this is in fact just repeating that vector there. But if you noticed, or if you recall from the previous section, wherein we defined the vector r to be the vector with the variables x, y, and z. So the vector r is x, y, z, and we can do one of two things. If we differentiate r with respect to t, then the derivative of the vector r with respect to t will be x dot y dot z dot. However, if we differentiate the vector r with respect to s, we get dx ds, dy ds, dz ds. So that this is then what can be written as the grad of phi dotted with a vector differentiating the vector r with respect to the arc length variable s. So it's clear that we can do that. Well, this is also interesting because if you recall that this vector, if it is written in terms of t, this is in fact how we did the actual derivative. So this was, just to spell out what we did the last time, this is the r dt divided by the s dt. And ds dt was the mod of r dot. So essentially this was what we called the unit tangent vector previously. So this was just recalling what we had previously. So that i.e. what we have is that d phi ds is equal to the grad of phi dotted with the unit tangent vector, the unit vector u, or in general the unit vector u. We use this to define what we mean by the directional derivative of phi in the direction of the unit vector u. So that in general what we say is, therefore, just to put it in words, in general we say that the directional derivative, you can regard this as a definition if you want, the directional derivative of the function phi, remember phi is here a function of x, y, and z, the directional derivative of the function phi, and this is important, that the directional derivative is, as the phrase suggests, in the direction of some vector. The directional derivative of phi in the direction of a unit vector, in the direction of the unit vector u, and I emphasize this is a unit vector u, is then written as d phi ds. That is d phi ds, which spells out as the grad of phi dotted with the directional vector. So this is in essence the definition of the directional derivative in the direction of the vector u. In particular, of course, we could take the direction vector to be the vector ijk, in which case the directional derivative reduces to your partial derivative. So this is in a sense like standing on some hill at some point, and if you look at the various directions, the slopes are different. So what you would expect is that if you choose a specific direction, you would get a specific slope. If you change your direction at the same spot, you'll get another slope, etc., etc. And this is in a sense the definition of the directional derivative. Let's do some examples. So, some examples. The first of which is a rather straightforward one, in which you are given the function phi. Well, let's suppose phi is given by the function of three variables, x squared minus yz. So that's x squared minus yz. And what we want then is the directional derivative of this phi at some point in a specific direction, right? And what we want, let me say what we want. We want the directional derivative, let's abbreviate as the directional derivative, the directional derivative of phi at some point, and this point is of course in Cartesian coordinates x, y, and z. So this is at 3, 1, minus 3, and of course this is a point then on the surface in the direction of some given vector, in this case 2, minus 2, 1. Okay then, for the directional derivative, if you look at d phi ds, that is what we really want. We need the grade of phi. So for this function phi, first of all, the grade of phi is the vector given by the differentiation. Derivative of phi with respect to x is 2x. The partial derivative of phi with respect to y is minus z. The partial derivative of phi with respect to z is minus y. This grade phi needs to be evaluated at the given point 3, 1, minus 3, i.e. x equal to 3, y equal to 1, z equal to minus 3. So at the point with coordinates 3, 1, minus 3, the grade of phi is then given by, if you put x equal to 3, this will be 6. If you put z equal to minus 3, minus z would be plus 3. And if you put y equal to 1, minus y would be equal to minus 1. So that will be the grade of phi. Now we need a vector u. We are given the direction 2, minus 2, 1. The vector u will be the unit vector in that direction. So the directional derivative, at least the unit vector u, will be equal to the vector 2, minus 2, 1 divided by its magnitude. That will guarantee that the vector u is a unit vector. So it's a vector 2, minus 2, 1 multiplied by, or rather divided by its magnitude. So this will be 1 over the square root of, well, the magnitude of this vector will be 2 squared minus 2 squared plus 1 squared. So that's 4 plus 4, that's 8 plus 1 is 9. So this will be the square root of 9. That's the magnitude of 2 minus 2, 1. So that this is equal to 1/3 2 minus 2, 1. So it's clear now what the grade of phi will be, at least the directional derivative of phi in the direction of the point, in the direction of the vector u. So that therefore the d phi ds, the directional derivative of phi, is then given by the grade of phi, and that's hidden at the back there. That's equal to 6, 3, minus 1, that's grade phi. And that we dot with the vector u, and the vector u is the vector with coordinates 2, minus 2, 1 divided by 3, etc. Well, this is 1/3, and if you multiply the coordinates, add them up, you get 6 times 2, that's 12. 3 times minus 2, that is minus 6. Minus 2 times 1, that's minus 1. So that's 1/3 of 12 minus 7. So that's 1/3 of 5. So that's basically 5/3. Now in the second example, we will choose phi as above, but we want, and this one is stated in a slightly intricate way, we will determine the grade of phi in the direction of another vector. So we want phi is above, and we want the directional derivative of phi, which is d phi ds. We want that at a point, at the point with x coordinate 1, y coordinate 1, z coordinate 1, in the direction of, in this case we are not given a vector with numerical form, in the direction of some vector given in terms of a path, in other words in terms of a parameterized path. So we want the directional derivative in the direction of this particular path, which is a parameterized path cos t, e to the t, 3t plus 1. Okay. So to determine this, we first of all need the t value. We're going to need this at some point. We're going to need the t value at which we obtain the point with coordinates x equal to 1, y equal to 1, z equal to 1. Right. First of all, let's just recall that the grade of phi, let's recall from above, that the grade of phi is as before, given as 2x minus z minus y. But the grade of phi at the point with coordinates 1, 1, 1 is in this case going to be equal to 2 minus 1 minus 1. This is at the point 1, 1, 1. So we got that sorted out. Now we need to construct the direction vector, which is the vector u. Right. Now we want the direction to be in the direction of a parameterized curve. So you need to keep this in mind that when you are given, or you need to choose the direction in the direction of a curve, what you actually want is the derivative or the tangent to that curve. So the direction of this path vector r is actually given by the tangent to the path. So let me spell that out. So the direction of r, vector r, the direction of r is in fact the tangent vector of r is the vector r dot, where dot is derivative with respect to t, i.e. the vector r dot, you differentiate with respect to t, is given as minus sine t, e to the t, derivative of e to the t is e to the t, and the derivative of 3t plus 1 is 3 plus 0, which is 3. We need to first of all determine the value of the vector r dot, specifically at the point 1, 1, 1. 1, 1, 1 are the x, y, z, and z coordinates. So we need to determine the t value that gives us the point 1, 1, 1 from the vector r. So first of all, let me say that. So from vector r, 1, 1, 1 is obtained by a specific value of t, is obtained by, it's clear if you do this by inspection, by t equal to 0. If you substitute t equal to 0 in vector r, you get 1, 1, 1. This is then the t value that we would substitute into the vector r dot to get the direction. So then vector r dot will be equal to, for this value of t, will be equal to minus 0, which is 0, e to the t, which is e to the 0, which is 1, and the third coordinate is just simply 3. So at t equal to 0, r dot is 0, 1, 3, which is not a unit vector. Therefore, the vector u is going to be equal to this direction vector 0, 1, 3 divided by its magnitude. So it's 0, 1, 3 divided by the magnitude of 0, 1, 3. The magnitude of 0, 1, 3 is the square root of 0 squared plus 1 squared plus 3 squared. So that is 10. So there's the vector u, the direction in which the grade of phi is determined. So d phi ds then is the grade of phi dot vector u, i.e. the vector 2 minus 1 minus 1 dotted with this vector u. So then therefore d phi ds is equal to grade of phi, which is 2 minus 1 minus 1 dotted with the vector u, which is 0, 1, 3 divided by the square root of 10. That guarantees that we have a unit vector there. So this is then 1 over the square root of 10 into 2 times 0 is 0, minus 1 times 1 is minus 1, minus 1 times 3 is minus 3. So this is then minus 4 over the square root of 10. That completes the second example for our directional derivative. Now, if it turns out that the equation of a surface or a function is given implicitly or explicitly in terms of z, then we have the following before we determine directional derivatives. So just a note, very important note, that if we have z being equal to some function of x, y, example, z equal to say x squared plus y squared. If you may recall, this was the circular paraboloid surface. Or if we have some function of x, y, and z, or for example, let me put this in the form of an example to make it clear. We have x squared, just an example, plus y squared minus something like z squared equal to a constant. Then we may define a phi in the following way. Then we define phi in the following way. Then define phi as. So the important thing is we're actually choosing what phi is. Then we may say that in the first case, in that case, we can say phi to be equal to the z of x, y minus z. So by choosing this example here, we can say, we just take the z to the other side, we can say x squared plus y squared minus z. So that here we would get the grade of phi being equal to 2x, in this particular example 2y minus 1. So we'd always get the last coordinate to be minus 1, just in the way we've defined it. In the second case, however, we can say that's For example, in this second case here, we could say let phi be equal to, take everything to the other side, as x squared plus y squared minus z squared. You can put k equal to 0 or just include the k, it wouldn't change the value for grad phi. So that here, grad phi, the gradient of phi, would be 2x if you differentiate 2y minus 2z. And this just, of course, is a specific example. This is peculiar to this example. So just keep that in mind as an important note. Right. Yes, as a result of this discussion, we need to just keep in mind the following corollary. And the corollary of our initial theorem on the directional derivative, which essentially is a definition, that the vector, or let's just call this a corollary, that first of all, that the grad of phi is normal to the surface. The grad of phi is normal to the respective surface, is normal to the surface. And secondly, that when the equation is given explicitly, if z is written as z of xy, like z equals x squared plus y squared, then the normal, of course, that's a consequence of part 1, right? The normal is the grad of phi, which in this case would be the derivative of z with respect to x, the derivative of z with respect to y. This is essentially what we determine, and the derivative of z with respect to itself is minus 1. And we'll put all this information into a particular example soon. Now another corollary which one needs to keep in mind is the following. And this corollary deals with the maximum value of the directional derivative. What it says is that the directional derivative has a specific maximum value which happens to take place in a specific direction. So if we just look at let's do the calculation first. You recall that d phi ds is the grad of phi dotted with the unit vector u. So this is the directional derivative of phi in the direction of the unit vector u. So this is then, if you spell this out, one way of doing this is to remember the alternative definition of the dot product of two vectors is that this is equal to the mod of grad phi. This, if you recall this from first year, this is the mod of grad phi multiplied by the mod of u multiplied by the cos of the angle between the two vectors. This comes from some way back result. Let me just record it there. That the vector A dot vector B is also equal to the magnitude of A, the magnitude of B, the cosine of the angle between A and B. So if this is your vector A, that's your vector B, then theta is the angle between A and B. So this comes from that. So it's clear that since cos of alpha is between minus 1 and 1, the maximum value will be achieved when cos of alpha is equal to 1. and cos of alpha is equal to 1 when alpha equals 0. The mod of u is the magnitude of the vector u, which is equal to 1. So that, therefore then, the maximum value of the directional derivative let me say that nicely, of the directional derivative is very simply the mod of the grad of phi, because the mod of u is 1, cos of alpha's maximum value is 1, and this is obtained in the direction of grad phi itself. In the direction of grad phi itself, not just any old vector u. So it's in the direction of grad phi. Grad phi, remember, is a vector. And let's do one last example that puts some of this information together. So the example goes like this. It says, let's put this in the form of a question. It says, find a unit normal, that means a normal of a value of magnitude 1, find a unit normal to a surface, and this is the hyperboloid of one sheet. You may remember what the hyperboloid of one sheet was when I discussed sketching these three-dimensional surfaces to the hyperboloid. And this is the hyperboloid, let me emphasize, of one sheet. There are two, one is with one sheet and one with two sheets. Of the hyperboloid x squared plus 2y squared minus z squared equal to a positive constant, let's say 8. So we want to normal that at a specific point. This point, chances are, lies on this surface, so it's 1, 2, minus 1. If you put the values of x, y, and z as 1, 2, minus 1 respectively on the left-hand side, you should get 8, which means this point is on the surface. And this sounds a bit new, and we want to, and the equation of the tangent plane at this point, and the equation of the tangent plane at this point. Okay. Let's recall what the surface looks like. So it's the hyperboloid of one sheet. You may recall that the hyperboloid of one sheet had a general shape like so. The outer surface of this structure are hyperboloids. The cross sections are ellipses. So that would be the z direction. And of course the x and y directions are the other two directions. So somewhere on this surface is this point here with coordinates 1, 2, minus 1. And what we want is a normal at that point. That would be, if you drew the tangent plane at that point, the normal would be perpendicular to that point. So what you have is, at that point, you might have a plane of that type. This is the same point, and you have this, which is essentially perpendicular at that point. So that's perpendicular. And sometimes we denote this as n. So what we want is this unit normal. Okay, so first of all, the grad of phi, if we need to define phi, of course, I said previously that if phi is not given, we can take everything to the left hand side and define that as phi. So you may want to say let phi be equal to x squared plus 2y squared minus z squared minus 8. You can exclude the 8. The grad of phi, therefore, will be given as 2x 4y minus 2z. That's a derivative of phi with respect to x, y, and z respectively. That's what we get. We need to evaluate this specifically at the point 1, 2, minus 1. So x equals 1, this will be 4. Y equals 2, so this will be 8. And z equals minus 1, so this coordinate will be 2. That's at the point 1, 2, minus 1. Now we mentioned that the grad phi was served as a normal to the surface. So the unit normal will be this grad phi divided by its magnitude. So one way of doing this is you could remove 2 as a common factor, etc., etc. But what we would in fact do is just determine what the unit normal will be directly. So therefore, the unit normal will be equal to this vector 4, 8, 2, if you want, divided by the magnitude of this vector 4, 8, 2, which is 4 squared, etc., etc. 4 squared plus 8 squared plus 2 squared, which I will just write the simplified form. You get eventually, you may show that this is 1 over 3 root 2 into 1, 4, 1. And you can check that this is in fact a unit vector. It's a unit vector that is parallel to grad phi, and since grad phi is a normal, this vector n will be a normal too. So the two vectors grad phi and n are obviously parallel. The difference is n is of magnitude 1. So we have the unit normal at the point with coordinates 1, 2, minus 1. Now we need some first year algebra. To determine the equation of any plane, recall from first year, requires two things. So suppose this is a plane. If that is some point on the plane, P, what we need is a normal to the plane, that is a vector that's perpendicular to the plane, and the coordinates of one point that the plane passes through. If you have these two things, you can write down the equation of the plane. So let me say this. Let me repeat. To find the equation of any plane, you need a normal to the plane and one point that the plane passes through. You need these two things. And you can very easily write down the equation of the plane. So I'm going to recall this from first year. So from first year, if you have the normal with coordinates, say, n1, n2, n3, and if the plane passes through the point with coordinates a, b, c, then one equal form of the equation of that plane would be x minus, now writing down the coordinates of the normal, so it's x minus a, y minus b, z minus c. That's a vector dotted with the coordinates of the normal, n1, n2, n3 equal to 0. So this is then the equation of the plane. This comes from first year. So in this example, what this means is, therefore, the equation of the plane finally, therefore, the equation of the plane is x minus, we're now writing down the coordinates of the point, so it's x minus 1, y minus 2, and z minus 1, which is z plus 1, and dotted with the coordinates of the normal or a factor of the normal. So it could be 1, 4, 1. I may or may not divide by 3 root 2 equal to 0. And if we had to expand the dot product we've just written, what we have is, we'll end up with x plus 4y plus z equal to 8. Ta-da.